Try some of these difference of squares again. If we see two terms and they're being subtracted and we think we can square root them, we will factor that into the square root of the first term, whatever that value is, plus the square root of the second term, times the difference of those two square roots. So our two factor binomials are going to look exactly the same, but one has a plus sign, one has a minus sign. So let's try this. Square root of b squared, I see two terms are being subtracted. The square root of b squared is b. And it's important that the square root of the first term goes first in each of the parentheses. Square root of 36 is 6, so we'll go plus 6 minus 6. If you FOIL this back together, you would get b squared minus 36. But wait, what about these? Well, you get 6b and negative 6b. And those combine to 0. So that's why you get that answer. Two terms being subtracted. Square root of 2, square root of 4 is 2. Square root of c squared is c. Square root of 121 is 11. So 2c plus 11, 2c minus 11. Give it a hug. Boom. Let's keep rolling with this. Two terms being subtracted. Square root of 16x squared is 4x. Square root of 9 is 3. So 4x plus 3. 4x minus 3. Boom. Square root of 169, I believe that's 13. Check it out. Square root of 1 is 1. Square root of 9a squared is 3a. So this 1 has to go first in our factored form. And the 3a is the square root of the second term that has to go second. This way, we get a negative 9a squared, which is what we have up here. And this way we get a positive 1, which is what we have up here. Oops, that's a duplicate. Thought those looked familiar, eh? So here, square root of 49a is squared is 7a. Square root of 9 is 3. So add 3 and subtract 3. I think these are both perfect squares, so I'm going to proceed with square rooting each one of them. Square root of 81s squared is 9s. Square root of 16t squared is 4t. Not the number 40, 4t. But 13. Square root of 64 is 8. Square root of u squared is u. Square root of 25v is 5v. There we are. Number 15. Ooh, number 15, square root of 2. That's not a perfect square, nor is 18. Is there some GCFs here we can factor out? So numerically, I will factor out a 2. Notice these both have the same bases, a to the 4, a to the 2. So we'll factor out the lowest degree that they all have, which is a to the 2. So then, our 2a squared comes out in front, our GCF comes out in front. What do we have left then? Just a squared for the first term and 9 for the second term. So now we try to continue factoring what's left in the parentheses. Yeah, can't we square root both of those two terms that are being subtracted? So this is just like the problems up in front. It's just that we have a GCF in front of it that we keep on bringing along. So, oh boy. So, square root of a squared is a, square root of 9 is 3. But make sure you bring that down. It's not correct if you forget to bring that down. So the just important factor is these two things over here. Ooh, 17's fun. First thing I'm noticing that, well, I get really attracted to high exponents, so I'm going to be able to factor out something because they both have the same base of r and the smallest degree is 2. If the directions say to factor, folks, even if you can only pull out a GCF, that's still factoring some of it. So I'm excited that I can at least do that. But since there's two terms that are being subtracted, I want to try to create perfect squares. And the GCF of these two numbers is 2, which also creates perfect squares. So 2r squared comes out in front as the GCF. We're left with 25 r to the 6th minus 16. So same deal as last time. That's great that we factor out a GCF, but let's try to keep going. Can we factor what's left in the parentheses? Yeah, so the square root of 25 r to the 6th is 5 r to the 3rd. So what that means is, what is 5 r to the 3rd squared? Well, I hope it is 25 r to the 6th. A lot of you are probably believing the 25. But remember here, when we're taking an exponent to an exponent, we multiply the exponents. So 5 to the second power is 25. R to the 3rd to the second power is r to the 6th. If you don't like that, think about it as r to the 3rd times r to the 3rd. You've got 3 r's times 3 r's, that's r to the 6th. So long story short, 5r to the 3rd is the square root of that first term. Then we're going to have minus 4 and plus 4, or vice versa. Don't forget your GCF. Number 20, folks, is kind of interesting. So here you definitely need to factor some stuff out to create perfect squares. Square root of 361, I think that's 19, double check. 9 times 9 is 81, so it ends in a 1, so I'm pretty sure it's 19. And 20 squared is 400, which gets you pretty close to that. Double check that. Here we got a couple issues. Can't square root w to the 3rd. This one has a w, so you're probably thinking, I need to factor out a w. That's a good thought. However, do you notice anything different or not cool about the signage here? The signs of these two terms? This one's supposed to be positive, and this one's supposed to be negative. So let's divide by a negative, right? We've done that with factor by grouping to switch both of the signs. So we're factoring out a negative w. A negative divided by a negative is a positive. I'm taking one of the w's away from the exponent of 3, so that's w to the 3rd. Here, the w's are canceling out or becoming 1, but then a positive divided by a negative is a negative. Oof. From here, folks, though, so I like the square root of, or I like square rooting w squared, that's w, but square root of 40, that's not factorable any further because square root of 40 is not a perfect square. So we had a good start on that one. That's all we can go. We can't make stuff up. Oof, that's half of your assignment all done.